Hey, hello. We're going to look at combinatorial results. I have 3 videos with different types of counting processes and finding probabilities. The first one is N choose K, and there's 4 different ways to do that. You can assume that you have an ordered sample, and then your sampling is with replacement, ordered, and then without replacement of your sample, and then you can do an unordered sample without replacement and an unordered sample with replacement. We're going to look at each 4 of those. And the 4th case, the unordered with replacement, is not widely as known as the other 3. And one of the main reasons I'm doing this video is the proof of that 4th one. It is so cool, and someone is so creative in thinking of it. But anyway, I'll just jump right in. First of all, we have to briefly talk about the fundamental principle of counting. And that says if you have A ways of doing something and B ways of doing another thing, then there's A times B ways of performing both, okay? And that can be expanded to, let's say if you have a task T, but it has to be carried out in subtasks. It's called TJ. And there's K subtasks. And each subtask has NJ ways to perform. So that means the total number of ways to perform task T is the product of the number of ways to do each subtask. Okay? I'm not going to prove that. I think it is pretty straightforward. Very quick example, if you have 5 suits, 3 pairs of shoes, 2 hats, then you have 30 different ways to get dressed, because each subtask, you just multiply them together and you have it, okay? So now let's jump right into the probabilities that I want to show. So we have an urn that has n distinct numbered balls. And we're going to take a sample size of K, okay? So the first one, in an ordered sample, that means if you take, let's say, a sample of size 2, and you draw a 1 and then a 2, that's going to be different than if you draw a 2 and then a 1. We consider those different samples, and that's called an ordered sample. An unordered sample means, hey, you got a 1 and a 2, it didn't matter the order. It's an unordered sample. So in an ordered in an ordered sample, we're going to draw K balls with replacement, and there's n raised to the K different ways to do that. Okay, I'm going to prove these after I tell you each. And then the number of ordered samples without replacement is going to be this, n factorial over n minus k factorial. Some often call this permutations, n choose K. And now we have an unordered sample, and then again, this is where we're just looking at, the number of balls in the samples. Hey, we got a 3, 5, and a 2. It doesn't matter what order we got them, we drew them in. Those are in our sample. Okay, so these are unordered without replacement, and this is the formula, and this is widely known as combinations, n choose K, and this is the standard formula. And it's this 4th one that I think is not known as much, and the proof of this is just, to me, it just was mind-blowing how clever it is. And so this is the formula for unordered with replacement. Okay, so let's jump right in on the proofs of these. So the first one, we have, let's say that these are the boxes that after we draw, we're going to place them in these boxes. We have n balls to choose from, so there's n ways to fill this. We place the ball back, and then we randomly pick one, and there's n more ways to fill this box, and we do that for each K box. So the number of ways is n times n, and there's K of them, so it's n to the K. So using the fundamental principle of counting, this is the result. Now, in this one, it's again an ordered sample, and but it's without replacement, okay? So here, in the first box, when we can randomly pick a ball, one of the n balls, and there's n choices to pick from. But for this one, once you've chosen one of them, there's only n minus 1 left. So there's n minus 1 ways to fill this box. And then once those two are chosen, then there's only n minus 2 ways to put a ball in this one. And then you go down to your k boxes to fill, which means you're taking a sample size k, and there's only going to be there's n minus k minus 1 ways to, balls left, so that's how many ways to pick it. So it's actually the product of these, and that's your answer. But there's a more convenient way to write it. So if you take this product and put it in this form, and then also take it times n minus k factorial, that means go down to 1, then this numerator becomes n factorial. Then of course if you multiply it, you have to divide it, because you're ultimately multiplying this number, what we want, by 1. And then that breaks down to n factorial divided by n minus k factorial. And that's what we often call permutations. Okay. So now in number 3, we're having unordered samples without replacement. Okay. So again, we're in this setting, we're randomly picking balls here and putting them in. And we know the number of ways to fill each box. Okay. But that is for ordered samples, okay? So if we have a 5, 2, and a 1, it's going to be the same as if we have a 1, 2, and a 5, okay? So what's the number, once we've picked our sample, what's the number of ways to rearrange these K balls? That's how many duplicates we have with this same K set. And that's k to the factorial ways to rearrange these using the same balls drawn. So we're going to take the total number of ways to draw k balls, but we're going to have to divide out the number of duplicates, which is k factorial. Okay, so what that says is the number of ways to draw these balls is permutations n choose k, but divide out the number of duplicates, which is k factorial. And then n factorial over n minus k factorial is permutations, n choose k, and we're dividing out the duplicates. Well, this formula is what we set out to prove, and this is the often called combinations, n choose k. Now this next proof I think pretty neat. So we have n balls, okay, and we're going to add to those n balls k minus 1 more balls, and we're going to label those balls. See, because the balls already that were drawn from are labeled from 1 to n, and we're going to label these new balls R1, R2, R3, R4, all the way up to R k minus 1. And then we're going to sample the K balls from all of those without replacement. And the number of ways to do that is n plus k minus 1 divided by k. Okay, so this is actually what I want to show you why this is the correct answer. But these balls, that R1, R2, if we get one of those in our sample, that's going to stand for repeat the lowest number and replace this ball with it. This one is going to be repeat the second lowest. So the second lowest ball in our sample, we're going to replace that number with this, put it in place of this. And we're going to do that for each one of these, okay? And let me give a quick example, okay? Let's have 4 balls. We're going to sample 3 with replacement, okay? And so the formula I'm claiming is there's 20 ways to do it, okay? Now, it says take the 4 balls and add 2 more, k minus 1 more. But if we kind of start back from scratch and assume these two are not there. And then we just generate a sample space based on these 4 with 3 replacement. We could draw a 1, a 1, a 1, a 1, 1, 2, a 1, 1, 3, 1, 1, 4, 1, 2, 2, 1, 2, 3, 1, 2, 4. You know, we could generate all possible combinations that, you know, for this setting. But then we have to develop a formula to calculate how many ways that is. And that's not exactly straightforward how to do that. Because then if n is 5, generating those is pretty darn tough. But if we use this method up here where we add k-1 balls labeled R1, R2, and then sample these without replacement. So once we draw it, then we're not putting it back. And so let's look at the number of ways to do this, okay? And this is without replacement. So we could draw a 1, 2, 3. Or we could draw a 1, 2, 4, a 1, 2, R, a 1, 2, R2, a 1, 3, 4, 1, 3, 4, R. And we could do that for all the possibilities. And we end up with a 1, R1, R2. And then we start with these, the 2s, 2, 3, 4, 2, 3, R1, 2, 3, R2, etc. Then we go 3, 4, R1. And then we end up with a 4, R1, R2. Okay, now this seems like an odd sample space, but remember the setting. R1 means takes the lowest one and replace it here. So this is really 1, 2, 1. And this one is 1, 2, 2. This would be 1, 3, 1, 1, 3, 3, all the way down. This would be 1, 1, 1. And then over here, this will be 2, 3, 2, 2, 3, 3, 2, 4, 4, 2, 2, 2, because this is the lowest and second lowest. And then you just do that, 4, 4, 4. Well, when you do that, you just created the sample space for what we thought of these 4 balls with replacement. That's the sample space. And it actually works for any n and any k. You generate the sample space for this. Well, we know the formula to draw 6 balls, and we know how to draw 3 balls, 6 choose 3 without replacement. That was the combinations formula, which is this. And so that's the answer to number 4. It's n plus k minus 1, choose k. You know, it's combinations, n plus k minus 1, choose k. And that's the answer. And this is only a heuristic argument. You could formalize it, make it in more detail. But that's basically what's going on and why that's the answer. Anyway, I hope you enjoyed it. I did. I love this proof, this argument, how to show it. My next video will be on n balls, putting, you know, n balls into k cells. How many ways can you do it? Or you can think of it putting n balls into k buckets or k urns. And we're going to look at a few different settings in there. That's the second video, and the third video is going to be just a general formula in counting and probability, and pretty exciting. So hope you enjoyed it. If you did, please like it, subscribe so you don't miss the next one. Thanks, bye.